So for problem one, the paintings are given in non-increasing order. The algorithm greedily fills platforms by adding as many paintings as possible without exceeding the maximum width. The total height is calculated by adding the tallest painting from each platform. So for the analysis, the correctness of algorithm one is guaranteed by leveraging the properties of monotonic heights and optimal substructures of the problem. Its time complexity is ON, making it highly efficient for the specific case. However, it doesn't work for general cases due to its reliance on the given height order, as we already demonstrated in prior counter examples. So for algorithm 2, the heights follow a unimodal pattern, so the algorithm processes paintings in two stages. It first handles the non-increasing sequence, then addressing the non-decreasing sequence. This transition at the local minimum is carefully managed to optimize platform assignments. So this algorithm also achieves ON complexity and is proven correct by adhering to the unimodal structure and maintaining the width constraint. However, its reliance on the specific sequence pattern limits its applicability to general cases. So, algorithm 3 employs a brute force approach, evaluating all possible platform configurations to find the arrangement with the minimum total height using a bit mask representation. It generates two exponent n minus 1 configurations and computes the height for each valid arrangement. While algorithm 3 guarantees correctness by exploring every possible solution, its time complexity, as listed in our project report, makes it impractical for large n's. It serves as a baseline for validating the correctness of the more efficient algorithms. Algorithm 4 uses dynamic programming. The DP array stores the minimum total heights required to arrange the first I paintings. For each painting, it considers all possible platform configurations, ending at I, calculating cumulative widths and heights to update DP. This algorithm achieves the specified time complexity, which significantly reduces the computational burden compared to exhaustive search. The correctness is guaranteed through the optimal substructure property. However, its cubic runtime can still be bottleneck for large data sets. So algorithm 5 builds an algorithm 4 by introducing optimizations to reduce the time complexity to ON squared. It uses pre-computed cumulative widths and limits and searches space for platform configurations. We implemented both a top-down recursive approach, program 5A, and a bottom-up iterative approach, program 5B. So for the analysis, for 5A, this algorithm ensures correctness through overlapping subproblems and optimal structures. The iterative approach, 5B, is more space efficient and performs better in practice due to lower overhead, as validated in our experiment. And overall, our contributions were for Program 1 and Program 4 that I wrote. And I also help with the
I am Stefania Alfonso, and I will be presenting the demo for the implementation of each program. Program 1. This implementation uses a greedy approach to sequentially add paintings to platforms until the width limit is reached. A new platform is added whenever the width constraint is exceeded. It calculates the total height and the number of paintings on each platform. This solution prioritizes simplicity and efficiency for cases with general constraints. Program 2. This program tackles the special case where painting heights follow a unimodal sequence, increasing and then decreasing. It combines a greedy strategy with a two-pass algorithm. The first pass processes from left to the peak of the unimodal sequence, and the second pass processes from the end backward to the peak. This approach ensures that the constraints are respected while minimizing platform heights. Program 3. This implementation uses an exhaustive search to evaluate all possible ways of dividing the paintings into platforms. By iterating over all potential splits using bit masks, it finds the configuration that minimizes the total platform height. This solution guarantees optimal results but is computationally intensive for large inputs. Program 4. A dynamic programming approach solves this problem by calculating the minimal height required to arrange the first type paintings. It uses a state DPI to store the minimal height for the first type paintings and backtracks to construct the platform configuration. This method balances efficiency and optimality, handling a broader range of inputs. Program 5. This program optimizes calculations by using efficient subrunge queries for maximum heights and widths. It precomputes or processes indices dynamically to determine the valid groupings of paintings. This solution leverages computational optimizations for handling specific problem constraints efficiently. Program 5b, a dynamic programming solution that minimizes total platform height while adhering to width constraints. It iterates through possible shelf divisions, tracks the cumulative width and maximum height for each shelf, and reconstructs the optimal configuration to return the number of platforms, total height, and paintings per platform. For my contributions to the milestones, I worked on programs 2 and 3 as well as the reports.
So looking at these charts, we can see that program 1 and program 2 are both scaling linearly with input size in terms of runtime, but program 2 appears to take a little bit more time than program 1. This seems to be consistent with smaller input sizes to larger input sizes. And the only time that seems like program 2 takes around the same time as program 1 is for very small input sizes, for example in n equals 1. In conclusion, the implementing program 1 was pretty straightforward since it was just a monotonically non-increasing order of painting heights. So program 1 used simpler logic, and that could explain why it took less time. Program 2, because it had a unimodal nature of the heights, required a little bit more logic, and that logic also resulted in longer processing times. Overall, the components also increased the understanding of greedy algorithms and emphasized the need of the importance of structures in algorithm design. Going over to milestone 2, we have a set of several charts. For example, we can see that the runtime for program 3, it's basically exponential. It's going up very quickly with input size. After 25 iterations, it takes minutes to process. But on the other hand, when you see program 4, you can see that it takes much less time to process and is able to handle much larger input sizes. So, and then if you look at program 5 as well, they all seem to be going in polynomial time. So comparing all the charts with this time in logarithmic scale, you can see that program 3's time is going increasingly in exponential, while program 4 and 5, A and B, are increasing in polynomial time. Specifically, when you look at program 5A and 5B, 5A seems like it takes slightly more time, but there doesn't seem to be a large difference between them. And then with the last chart, if you look at the output quality comparison between program 1, which just looks at a monotonic sequence, versus program 5A, which can look at any sequence, you can see that the program 1 outputs actually underestimates the size often, as you can see here, and it seems to usually underestimated by around 10% if you look at how it's progressing when the input size gets larger. So in conclusion, this experience allowed us to delve deeper into various aspects of algorithm design and optimization. For the initial programming tasks, each of the implementations largely depended on the clarity of the problem and approach taken. And we were able to test different kinds of programs, for example, ones that take exponential time and others that took polynomial time. So it also introduced the concept of handling multiple platforms and optimizing for total height, which required combining several optimization techniques. One specific challenge was managing the interactions between platform width and height constraints, which led us to require balancing between breaking the problem into manageable parts and ensuring an optimal overall solution.